Okay, thanks a lot. Yesterday I got to talk about rapidly rotating fluid dynamics, which might be occurring in a planetary core. Today I'll try to take the next step and get across ideas for how you actually get dynamo action in a planetary core. Okay. Oh, so I'm going to address questions I got yesterday that I didn't address. I got many questions either during or after the talk that I didn't address. I'm going to hit a couple of them just here and there. One of them I got, one question that was raised a couple of times was, how do we get funded just to do research on record players? We don't. Those are classroom demos you saw. You can buy a record player. You could do that yourself. It costs like $100 to set up. So for what it's worth, we actually have research class devices as well. It's not all record players. So we have right now the world's largest rotating convection experiment in water. And we have actually, I guess, the only rotating magnetoconvection experiment in liquid gallium. Grenoble's had one before, but I think they decommissioned it. And in addition, we have another way to study core flow would be mechanically driven flow. So here's a device that Alex has run for the last couple of years that librates. So it rotates and then it shakes. Lots of planetary bodies either precess, nutate, wobble, librate. And so then the question there is, can you couple that shaking to core dynamics? So here we have the camera in the rotating frame. I don't know if you can see it. A little bright in here. But when you simply shake a rotating fluid, you excite inertial waves. And if those waves basically nonlinearly interact, you can drive global scale turbulence in your flows. So we basically just talked about convection last time. I'll talk mainly about convection today, but there are other ways to generate turbulence in planetary bodies. So we study all sorts of ways to drive those kind of flows. Okay? But I do love record players, and we'll show it a few more record players, I bet, today. Okay, dynamo. We mentioned this last time. The key is, how do we convert kinetic energy into magnetic energy? We need a liquid of some kind, and it needs to have some finite electrical conductivity. If that's the case, it might be possible to get a dynamo. How do we do that? Mostly, the main tool right now is through numerical dynamo models where we solve these coupled equations, and they're moderately heinous. Typically, there's some energy source. In this case, I've just claimed it's temperature. That feeds into some form of buoyancy term. So there's a buoyancy term. That buoyancy term then drives a velocity. That velocity couples into something we'll talk about today, something called the induction equation. And that velocity will act and do work so that it can actually build up a magnetic field over time. Once you build up that magnetic field, that'll then drive currents and magnetic fields that will provide forces. Those Lorentz forces will typically back react on the velocity field, which will then affect the induction equation as well as possibly the energy equation. Again, misery. That's horrible. That's like the worst explanation ever. Except that is roughly what's happening. You have this massively coupled nonlinear system. So it gets a little hairy. So let's not talk about it. Let's just start off by trying to get a feel for MHD itself. Forget all that, right? That was horrible. Let's just look at this Lorentz force. Let's get a feel for that. I'm going to do one, again, kind of classroom class demonstration, hopefully to get you guys feeling the interaction between Lorentz forces in a continuum and the fluid mechanics you might get. We're not going to talk about dynamos, actually, when we do that. We're just going to try to get a feel for magnetohydrodynamics. Then after that, we'll go on to talk about dynamos. Okay? So first, let's just start basic. Let's say we have some particle. Nothing's acting on it. It'll just keep going at whatever velocity we give it. But if it flows into some region where there's a magnetic field, where let's say there's B coming out of the board, well, then there'll be, on that particle I, there'll be whatever its charge is, QI, it's got some velocity VI, there'll be a QV cross B force, right? That's the Lorentz force on a particle. Everybody knows that from freshman physics. And it'll cause the particle to be pushed off to the right. You might also notice that actually looks a lot like Coriolis force. So I kept talking about inertial circles yesterday. Yeah, this will also eventually, if that's the only, those are the only two things in the system, yeah, you'll get some gyro radius, right? Okay. Now, let's go into a continuum with many charged particles. Patrick actually just introduced this. Talked about current density. So the current density is now the number of charge carriers per unit volume in our continuum. Q is their charge, given them all the same charge Q. And now we're not worried about the individual velocities of all these charge carriers. We're taking the average over the volume. So now there's some net drift velocity. Okay? And if we work out the units, that ends up being the same thing as current per unit area, right? It's just amps per time through some cross-sectional area. Okay, so that's J. That's the current density in some volume. And if we then rewrite the top equation, we can write instead of mass, it's not mass of a particle, now it's mass of that volume of material. So it's rho du dt times whatever the volume is. And through that volume, again, we have so many charge carriers. They each have this charge, and they all have some ensemble drift velocity, right? They're all going this way and that way and that way, but on average, they're going in some direction, Vd. Well, okay, this is J. That is our current density. There's the volume again, and it's again crossed with B. The volume doesn't matter, right? That's, in a sense, arbitrary. So then we can drop that, and we see we just have rho du dt equals J cross B. So there's something really crazy that we kind of snuck in there. That velocity is the material velocity. Why? Why is it the material velocity? I mean, the forces were acting on the charges. So why is it a material velocity? It's weird. Okay, so it would be just that the charges were flowing if we had effectively a superconductor. We have anything but that. Everything's scattering like crazy. It's an incredibly messy system. So the forces are acting on whatever the charge carriers are, and the charge carriers are constantly colliding with things and scattering. There's tons of microphysics, and we've left all that out. But the end action is that the force applied to the particles actually is applied to the entire continuum. Okay? That's a weird and hard idea. Does it make sense? It's strange. If you were in a vacuum, that wouldn't be the case at all. You just have the charges go. But you're anything but that. Okay. So that's so darn spooky. Let's give an example. Let's maybe see if we believe that. I'm going to just do an MHD pump, and it's going to drive flow in a circle. It's a pump. It's going to drive fluid in a circular path. Sometimes it's called MHD Couette flow. I'll just call it an MHD pump. And so it's going to be steady state flow. We'll get rid of du dt, and instead we'll put a viscous force on to balance this weird Lorentz force. Okay. This is, I said, this is not a dynamo. This is the exact opposite of a dynamo. I'm going to impose a current density. I'm going to impose a magnetic field, and we're going to drive U. Again, why? Just to build up our intuition. Okay, so here's our MHD pump. There's a view of it. Top view, it's just an acrylic cylinder. It's one of the ones we used in all our other experiments. Same thing. But now we've put, I must have, good. So now in here we have a little bit of conducting fluid. So it's copper sulfate, just dissolved in water. There's not much of it in there, actually. There's a slight bluish tinge, but we didn't need to put much in. B is coming out of the board, so this is sitting on a plate of ceramic magnets, so outward magnetic field. We've got copper on these two cylindrical walls. So we just took copper foil and put it on the inside of the acrylic cylinder, and we bought a little copper ring on the inside. And then last thing we do is we hook up a power supply, one to each copper wall. And so we're driving some fixed amperage across that ring. And so it's going from the red lead to the black lead. And you might say, oh, it's just going to go in from red to black. But no, of course it doesn't. It goes in radially. It's copper, right? It goes in everywhere, radially inward. So you have an inward J, and you have B coming out of the page. So hypothetically, that should produce a force. J cross B, J, B is out of the page. It should be off to the right. So these charge carriers are all going to be trying to be forced to the right of wherever they're trying to go, inwards. And they're constantly, again, having all these microscale interactions. They're going to drag the fluid with them. Get it? They're really one and the same, honestly. So let's try it. So let's just run this thing once. Oh, I don't want the cross-section yet. Oh, wait. Before we get into that, I want to just play the damn thing. I changed my slides, but I forgot to include that. So, yeah. Okay, so let's just play it once, then we'll go back and do it again. Yeah. Okay, so here's the idea. So now, there, Lorraine just put in some food coloring like usual. Most of it fell through to the bottom. That dark spot is where it fell through to the bottom. The lighter stuff around it, that halo, actually got caught in the top surface layer. So that's great. We're going to then look at really the flow in that top surface layer. We're going to turn on the power supply. And there it is. And so we're going to pump the fluid with no moving parts, right? And it forms this beautiful spiral. And this is just because J is going in and B is out of the page. And I've got a conducting fluid. So, great. So that's my simplest, probably MHD problem we can do. Let's walk through it a little bit. Okay, so there's our pump. Let's take a cross-section through it. And so what do we have? We have the center of our cylindrical tank, some height of the fluid H, vertical B, and then we have J going inwards, right? We're driving it from the outer ring to the inner ring. And so here's where the interesting part of the problem comes in. J ends up being that current I over the cross-sectional area is flowing through. And the cross-sectional area is varying, right? The cross-sectional area is H, which is a constant, times 2 pi r. Well, that r is shrinking as you go inward, and so that means the current density is going up as 1 over r. Does that make sense? It has to. You're just sending so much charge through this volume of fluid, and as you go to smaller rings, the current density has to go up. Great. So now, these are not the right slides, but okay. So we're going to now, 1, sub in our value of J into this equation, and 2, we're going to make a thin layer approximation. We're going to say that H is much, much, much thinner than the smallest radial scale in our system, our inner, the inner radius of that inner cylinder. And in that case, you can throw out all those radial derivatives, and you can just write this equation that way. You have this Lorentz force, and again, J cross B, it's in the phi direction. It's azimuthal. And so it's going to be balanced by phi velocity and the Laplacian in only the z direction. Nothing else matters. And we can solve that. And so 1, we know we're just going to solve it. It's got a no-slip condition at the bottom. And so then the surface velocity, the velocity at h, just goes, bunch of constants, I, B, H, 4 pi, mu, we can measure all those, and 1 over r from the Lorentz force. So if we now look at this, let's look at it again. So we predict this U phi behavior, and roughly the inner radius is about half the outer radius. So the velocity near the inner cylinder should be about twice that at the outer cylinder. And in addition, the circumference at the inner boundary is about half that at the outer boundary. So I've got two factors of 1/2. So it should take about 4 times longer for the fluid to go around at the outside than the inside. So we can trace that. We don't need to see that. We saw that already. So now, when we kick this off, if all the physics is working correctly, the time it takes for the die to go around near the inner boundary, that should complete about 1 loop when the fluid near the outer has gone 1/4 of the way around the circle. Okay, so let's see if it works. Okay, there it is. Just turned on the amperage. And we measured all these things. The velocity works about right. And to get this beautiful shear flow, it is going faster near the inner boundary. You get a nice little boundary layer right there too. Cool. And when that goes around once, that die goes to about 90 degrees away from where it started. Okay, so it's a little spooky, but it's also kind of sensible. Any questions on that? Does everybody get it? You guys got to be kidding me. Yeah.
Did you say your solution was copper sulfate? Is your solution reacting with your copper?
Yeah, so that's one of the issues. That's why you have to use the lowest amount of copper sulfate you can, because you, in time, will start to basically plate onto the copper, and that will stop the current, right? So as you start to build crap up on the copper, your power supply will become unhappy, as far as I can tell. Something's building up on the plates. What is it?
Copper. You build up on one plate, and then you bubble oxygen on the...
Maybe it's just bubbles that's then stopping the current, but I don't think it would. But definitely we have to clean the copper about once a day. So maybe there's something else reacting.
Are you sucking the copper ions out of solution?
I don't know. Maybe. Honestly, I haven't worried about it. Okay.
John, why does the fluid concentrate in a narrow ribbon rather than kind of spread more uniformly?
So say that again. You mean why isn't the die diffusing?
Yeah. Why isn't it, as it rotates, why do you end up having like a very narrow spiral as opposed to...
I would argue, well, let's put it this way. So the advection time, this is movies in real time. So the time scale for this flow is maybe, 30 seconds? While if you take, I actually don't know what this is, maybe it's 2 millimeters thick ribbon, 2 millimeters, and take a diffusivity for some chemical composition. Oh man, even on that small 2 millimeter length scale, the diffusion time is going to be huge. So there's really no diffusion here. And so it's not diffusing. It's way too fast for there to be diffusion of the dye. And in that case, you're just shearing out the color, right? It's just this passive tracer that's not diffusing at all.
Or is it that you have an irregular starting face in your dye?
Say it again?
You have an irregular starting face in your dye.
Mm-hmm.
Another reason for that.
Yeah, I mean, yeah, you're right. The smaller the length scale you start out with, the more you'll shear it out. I'm simply saying there's no diffusion of that dye. You're just kinematically stretching it. Does that make sense?
So 2 questions. So at the beginning, when you derive... Oh, sure. And so 2 questions here. At the beginning, when you derive the electrical current, J, current density, J, you relate that to... you don't have to go back, yeah. And so you actually relate that to a velocity field, right? The velocity. That's actually should be drift. Supposedly that should be drift velocity for charges, right?
Mm-hmm.
Are you saying that velocity is the same as the fluid velocity?
No, sorry. Good
I think
question.
you use the same U.
Oh, no, my apologies. If I said that, that was a
Well,
misstatement.
or maybe
So-
I
so the-
misremembered.
No, so what's hidden in J is that drift velocity.
That's drift velocity.
And I'm
yes. But it's
imposing
not.
that here.
So that's not necessarily the flow velocity. Right?
No,
Okay.
no,
good.
the drift velocity is simply being imposed by the power supply.
So now for this experiment you just showed, I suppose without the B field, and then of course the current actually was just from outside, out ring to the inner ring, right?
Mm-hmm.
And now you got this, you apply this B field, and then you see this. Apparently there is this. You see this circling, because of the Lorentz force, right? And so then, what would be actually the electric current, your directions now?
I won't lie, I haven't paid attention to it. It's so small. There will be a secondary induced set of currents from the motions, but they're tiny. They're so small. This is why I'm saying it's the opposite of a dynamo. We are not generating current that's at all comparable to what we're imposing. They're tiny. I don't think we could measure them if we tried. Actually, we did try once, and we didn't measure anything.
Primarily caused by.
In this case, it's all caused by what we impose. That's why I'm saying, again, opposite of a dynamo, just to show a weird problem, but it actually works. I can't make a dynamo in the lab, honestly, but I can do this easily, and it's got all the physics.
Have you ever, so just a fun question with that last experiment, have you ever tried to flip the electrodes around after you
Oh,
did it?
yeah, that's actually part of that movie, but I clipped it because it was too long. So that's the next thing they did. It's what you have to do, right? The next thing you do is, I could show it if you want later, but the next thing you do is you flip the electrodes and it reverses and everybody in class goes, oh. And then the next thing after that is we add too much dye. We go, oh, let's try it again. And you add too much dye and then it just turns all kind of purplish. But yes, that is obviously the next thing you do. And the other thing we do is we'll run it not on the magnet. Because again, people tend not to believe this. So we'll pass a current through, there's no magnet, and everything sits there. It's unbearably boring. Right? You've just created a circuit, but nothing's happening magnetohydrodynamically. You need both for there to be forces in this system. So then we put it on the magnet, you get the flow, and then, you flip the leads, and it goes backwards. And if we did it really, actually a fun thing to do would be to do it super low current and to do the G.I. Taylor problem where you have kinematic reversibility. So one other comment on that, G.I. Taylor was mentioned by Patrick. He did fundamental work in solids. He's the same person who does our Taylor columns. So G.I. Taylor was just he ended up being pretty good at the science thing. But I love that. I mean, these connections are they're all sitting there. Okay, any other questions on this? Do you guys even get by it roughly? I think I heard a great question from you, because I think it sounds like I misspoke about drift versus flow velocities. The entire fluid reacts to that Lorentz force. But no, the drift velocity is not the flow velocity. My apologies. Everybody good besides that? Was that useful, or did that just confuse the living crap out of people? That deathly silence means it worked great. Okay. Okay, let's keep going. Okay, so that was the opposite of a dynamo. Now, let's start going to a dynamo. In a dynamo, it's just the opposite problem. Now we're going to impose U. We don't necessarily impose it in a planet, but given some U, we're going to try to figure out how to generate a self-sustaining electromagnetic system. So now we have to go back to our equations, but now we're going to focus on this induction equation. And I was going to derive it, but I don't think it's actually worth it. Again, if people want, we can do it at the end. Let's just play with it instead. So this is the equation that governs the evolution of magnetic fields in MHD systems. I forgot, in taking away the derivation, I took off for me one other important point. A lot of people ask, there's no current there. it's so crazy. But in non-relativistic MHD, so slow flow velocities, J is basically related to the curl of B. So they're structurally related. So you take a curl and you get J out of your system. You could make a very similar relationship by just taking the curl of the induction equation. Then it would just be an equation for J versus U. So you either do it for J or you do it for B. But you don't need to have both. So that makes it a very nice equation. And I'm going to argue you can compare it moderately well at 0th order to a scalar heat equation, which is much easier. So let's look at a heat equation and kind of use our intuition from a heat equation. First thing we'll do is we'll drop the source term. Let's drop that term all the way on the right. And these are comparable. If you look at a heat equation, now it's just a thermal diffusion equation, and you get some typical timescale tau over which the temperature field diffuses. It's your characteristic length scale, which comes from your Laplacian, and kappa, right? So L squared over kappa roughly tells you how fast temperature will diffuse in your system. Okay, well, so we can, scaling-wise at least, we can say the same thing for this nastier vector equation. But it works out the same way. Now it's length scale over the magnetic diffusivity, where the magnetic diffusivity is basically 1 over the electrical conductivity. And so we know the magnetic diffusivity in core-like fluids. It's of order 1 meter squared per second. And so if we put in 1 meter squared per second, and we take roughly the radius of the core, you get that the magnetic field, if there were no sources, the magnetic field would diffuse away in about 15,000 years or so, which geologically is smoking fast, right? So we need to maintain these currents. So to do that, we need our source term. And so again, just like in a thermal equation, you might have either some boundary forcing or some volumetric forcing. Okay, here we have some magnetohydrodynamic forcing. And it's a little nastier in that it's, again, a very complex vector source. It's curl of U cross B. And I'm not going to actually go into that deeply. I'm just going to show you what can happen. And first, I'll scale it. First thing, let's just worry about how the scaling works. So for a self-sustaining dynamo, that induction term on the left has to at least be able to exceed the diffusion term. If it can't, you're always going to lose out to diffusion, right? So if we just scale the right-hand term and divide it by the left-hand term, take all the gradients as 1 over L, B drops out, you're left with some characteristic velocity times L over eta. And that's called the magnetic Reynolds number. And so it's got to be about order. Theoretically, it has to be greater than pi squared, but realistically, it typically has to be greater than about 40 or 50 for dynamo action to occur. So what's that mean? So one of the things people kept asking me yesterday was, yeah, why don't you guys just build a lab dynamo? You noticed I don't have any. I have convection experiments and libration experiments. I don't have a lab dynamo. It's so easy to do these numerically. So I thought I'd briefly just mention that here. I'm going to argue a lot of it comes down to just RM, just looking at the magnetic Reynolds number. So if we take eta to be order 1, and if we take for our biggest lab experiments L to be order 1 as well, so 1 meter and 1 meter squared per second, if RM is going to be of order 40-ish, I need 40 meter per second flows. That's fast, right? That is pretty fast. But what you heard me say yesterday again and again is, oh, I need to really organize these flows into beautiful, coherent, structured helices, right? I need a lot of structure. It's really hard to have structure when you're cranking up the velocity to 40 meters per second. Okay, so, yeah?
And is this the velocity in the rotating reference?
That is the velocity in the rotating reference frame, yeah. That's the other problem is you can't rotate fast enough for the rotation to ever matter. So when you're having to go at those speeds, I don't know if even a rotating experiment's the way to do it. Very hard. So it is really hard to get these things to happen right now in the lab because liquid metals, honestly, aren't that good of a conductor. Ada's high, 1 meter squared per second. That's incredibly high. Yeah.
So here, can we use other materials? Eta has
Good
larger
question.
already.
So a lot of people are trying sneaky materials. They're trying to put in, they're trying to seed liquid metals with high susceptibility materials. People have tried a lot of things. So far, hasn't worked. But there's a guy at Yale, Eric Brown, who at least is making some headway. I would love that, right? That would be great by me. I say let's cheat to win, right? Let's do whatever we have to do, the materials, to make a material that would make the problem easier. That would be fine with me. But so far with just homogeneous standard liquid metals, you really can't get very far away from those values of roughly order meter squared per second, which is incredibly high. Okay, now let's go to numerical dynamos. What sets eta in numerical dynamos? Whatever you want. So we typically choose values that are about 1 million times higher for the electrical conductivity. And as this then goes down by a factor of roughly 1 million, great. It's easy. You can do nice slow flows. You know, my argument is if I could buy the fluid in numerical dynamos, I would get a teacup, I would stir it, that would make a helix, I'd get a dynamo. It'd be awesome. You can do the numbers. It would work great. So you get a teacup dynamo if you could use the fluids that we typically use. And we should. You know, there's nothing stopping us. To start getting at the physics, we might as well use a really good conductor. Not a superconductor, but a very good one. But the minute we go to the lab, we have to use real metals. And that causes complexity. Does that answer that question? Okay. Okay, so there's magnetic Reynolds number. Another thing to take away from magnetic Reynolds number, here it gets a little harder, but that source term, it actually is made of 2 parts. There's an advection term in there, and there's a stretching term. The stretching term grows the magnetic field. The advection term carries the field around. And so let's not worry about the source term for a minute. Let's just think about advection. It means at 0th order, at high RM, you might expect your magnetic field lines to somewhat be trapped in your fluid. So if the fluid's all moving in unison, you'll see the magnetic field carried. But if they're stretching in the fluid, if they're velocity gradients, then you'll start stretching apart the magnetic field, and that's how you create new magnetic energy. Okay? So 1, we can carry the field around. 2, when we stretch magnetic field lines, we can actually create more magnetic energy. Okay. So now let's start looking at the 2 main effects to build. I'm going to try to build the simplest possible dynamo mechanism that I can. Okay, so the first part is going to rely on what's called the omega effect. And this is where I'm going to put in some initial, in this case, poloidal magnetic field, poloidal being the aspect of the magnetic field that can basically cross the core mantle boundary. So this is the magnetic field we typically see. And so we've got some poloidal magnetic field strand there in green. And you can see it's got curvature, so it has some vector components out in S, right? And now I'm going to put on some zonal velocity, which means an azimuthal velocity that's got a shear in it. That velocity varies with cylindrical radius, kind of like what you saw with our MHD pump. Okay, so what's going to happen is the fluid here, let's say, is going, I don't know, let's say it's going faster, and the fluid farther out is going slower. What's that going to do? That is, in this stretching term, it's going to produce a new vector component in the phi direction. So it's going to carry the magnetic field off to the side. And the magnetic field can't break. So instead, as you stretch off to the side, you take a purely poloidal field and you tease it into an axisymmetric field. And you start to create a toroidal field, a torus, a field wrapping around in the interior. Does that make sense? So let's think of it again. Okay, here. So what the argument would be, let's just take a piece of taffy, and let's say that Shiji's holding it, and he's near the outer part of the core moving slowly, and I'm some piece of fluid at some higher azimuthal velocity, closer to the inner core. I'm holding the other piece of the taffy, and if I start moving off to the right, where it was originally all oriented, this is some vector, it was all originally oriented straight out of the board, but now as I move off to the right, it's somewhat trapped in the fluid. So as I move off to this side, that velocity shear is now going to connect it to here. Okay, well that vector now has a component that way, and it has a component that way. In addition, the total vector length actually, in a sense, it's grown. So we've created magnetic energy by stretching the fluid. That grad U creates magnetic energy. It does work against the Lorentz force. I haven't shown that in detail. But that's what's happening. Does that make any sense? I don't know if it does electromechanically, but that's what's occurring kinematically. Okay? So let's show that. Here's a nice schematic. Maybe it shows it better than my kind of mediocre schematic. Here's some poloidal field. And I set up some axisymmetric flow with gradients in it. I think the gradients are, in this case, they've chosen d omega. Omega is the angular velocity, d omega ds. So there's a radial gradient in the angular velocity, and you can see it starts wrapping up that initially purely poloidal magnetic field, purely coming in and out across the core mantle boundary. And now it's wrapping it up into a magnetic field that's mostly trapped inside the core. It's mainly toroidal, toruses. Yeah.
So can you explain again? I missed it. Why you have the gradient in the toroidal velocity?
So, good. So let's say I didn't have any gradients. Let's just say I had a solid body flow. Again, think of the magnetic field as somewhat trapped to the fluid. Not perfectly. If it's perfect, this actually doesn't work. Superconductors actually can't do this. But if it's a good conductor, then the magnetic field is somewhat trapped to the fluid. And now imagine the entire fluid is moving in essentially what's called solid body rotation. Right? It's the problem we did yesterday. I said spin the tank up for a long time. It's all at the same rotation rate. Now, let the magnetic field permeate that layer. It's not attached in any way outside of the core mantle boundary. We're going to argue that's all an insulating silicate at some level. And so now let's spin it. What's the magnetic field do? It all just spins as one. Am I doing any work on the magnetic field? No. Are there any Lorentz forces? No. Actually, nothing's happening. I'm simply moving around an axisymmetric field. It'd just be attached to me. I would look. You can see. Right? That's it. It's a delightful dance. Now, instead, if we could have this part of me, the outer part of me, going slow, and the inner part of me could be going faster, then imagine those field lines. We would start stretching them around my... And actually, that's exactly what there's tension in that. It takes work to do this. Not just for me, but you have to do work against the magnetic field. You can't just create energy out of nowhere.
But why do you have that gradient in the wave?
So I haven't told you why there's a gradient. I'm imposing that gradient. If you looked at Mike Hawkins's movies yesterday, you always get these shears. In core flow, you very often get large-scale shears. And so it's very natural to say, well, I'm just looking for mechanisms. One of them that's very natural is to have a shear flow. They often develop in these systems. Let's see what they do. And they generate, out of an axisymmetric shear, you get an axisymmetric field. That's awesome. Yeah?
So I'm trying to imagine these numerous vertical columns.
No, we're not there yet.
Okay.
No columns yet. We're doing just large-scale flow. We'll get to the helices.
And you'll have multiple toruses, right?
We'll get to it. Very nice question. I'll get to it in a minute. But let's do one more thing here first. And then I'm going to go right, and then I'm going to start stepping towards that. So purely axisymmetric omega effect. I take an initial poloidal field. I wrap it up on this spindle, and it gets all, and now I've got a strong toroidal field. Well, notice one other thing. What happened over time in this system? I generated from a poloidal field a strong toroidal field. Did I do anything to regenerate my initial poloidal field? No. So how fast should it be decaying? On some time scale tau, in like 15,000 years. So that's what's happening in this wonderful diagram that I have no idea where I stole from many years ago. You've got some initial poloidal fields, got a good amount of energy, couple field lines. You wrap them up into a torus, but look, they're going away. That original poloidal field, I haven't done anything to maintain it. Axisymmetric motions don't help regenerate that component of the field. So look where we end up with at stage at image 4. You got a nice toroidal field, but actually the poloidal field dissipated while that happened. So if we just keep that axisymmetric shear going, are we going to have a self-sustaining dynamo? No. Why? Because this process takes a poloidal field and generates a toroidal field from it. Okay? But it doesn't regenerate the initial poloidal field. So if we just kept this going forever, well, actually, this would then dissipate next. If we had no other process, QMAT, if we had no other process, this would then dissipate away ohmically. Does that make sense? I can keep, once it's toroidal, then, actually this relates, I think, to your question, Jerome. So once it's toroidal, and I just have axisymmetric shear, then these loops just get carried around. But I'm not doing any work on the loop. Anywhere it is, it just gets carried around. And if those are different speeds, it doesn't matter. It's just going to get carried around in an axisymmetric sense. So it has to then dissipate away. Once there's no poloidal field, this effect doesn't do anything. Does that make sense? That's the first stage. Yeah?
So moving from your first cartoon, the poloidal cartoon, we've got 4 field lines, and then by the time we get to the end, we have nothing sticking out, so you've lost your poloidal field.
Boom.
Have you had to break field lines? I'm under the impression that's a bad thing to do.
No, they haven't broken.
Have they been pushed out then?
They've actually diffused away. How do you think of it? Do you think of them being pushed out? I really think of them as simply diffusing to zero. Just their intensity is becoming smaller and smaller. I haven't thought about pushing or not pushing. You can really just leave them there. And that intensity of that current system is going to zero because you're in a resistive fluid. I don't know exactly. Honestly, I've never thought about how it diffuses away. I won't lie to you. But you could solve that diffusion equation for whatever J. You know, that has a toroidal, this is what's spooky. So in MHD, J, this is important, I took this out, mu naught J equals curl cross B. So that means if you have a poloidal J, it means J and B wrap around each other. And so if you have a poloidal magnetic field, it means that's being maintained by a toroidal current system in the core. So you'd solve that diffusion equation for that current system. Nothing's maintaining it. It's going to diffuse. You get it? Any other questions on this? This is the first stage in getting a dynamo. Okay? Now, the next part. Now we need what's called the alpha effect. Here's where we have our helices come in. So here's where Matt comes in. So now, I'm not actually drawing helical columns in here. It's not the greatest drawing. But I'm simply applying a local helical motion to a toroidal magnetic field line. So I've got that blue magnetic field line. And at some point in time, I assume there's helical flow right there. What's that going to do? The helical flow pushes up the field line and twists it. And let's say, somewhat naively, that it twists basically so the loop is now perpendicular to the direction of the original toroidal field. So now I've got a loop of B, a loop of magnetic field, with the face of that loop really pointing that way in a right-handed sense. Well, J has to come out of that loop. Remember, J and B wrap around each other. So when I make that loop, I've got a little current system coming out of that center of that blue loop. And it's going now in the azimuthal direction. And now let's say I had these helices everywhere along that loop. Then I would build up an ensemble of little pink J's going toroidally. Well, now if I can get this through this non-axis symmetric ensemble process, if I can build up a bunch of those, and I build up this big, now toroidal current loop, well, a toroidal current loop produces a poloidal magnetic field. So somehow I have to break axis symmetry. Maybe the best way to do that is with helices. It's not actually maybe. As far as I can tell, you always need some helicity. And so now that you've had these helical motions warp that initial toroidal field into all these little structures, then you regenerate a poloidal magnetic field, and now you can start the process over. Did I spell something wrong? Where are we? Is this a spelling error? That's called a spelling error. Okay.
Our question is, so in the previous slide, that we also have the toroidal magnetic field. So the previous slide, is there also currency in the loop or not?
Say it again. Wait, so previous slide. This slide?
Yeah, and the bottom one.
So this is the last stage of my omega effect. If I just have an axisymmetric omega effect, then I end up with a purely toroidal field. But now I've lost my source field, which was poloidal. So I need to regenerate that poloidal field. And what I'm trying to say is the way you do that is somehow with helical non-axisymmetric motions. And so hidden in this is a takeaway is that you can't generate an axisymmetric dynamo. That's an old theorem from Cowling. You can't do it. You need some non-axis symmetry in your system. It may be small-scale helical turbulence. You may not ever see it, but you have to have it. Okay? And so here we've got an axisymmetric toroidal field, and now these non-axisymmetric helical flows, taken on an ensemble sense, hopefully on average, generate a toroidal current system. That gives you back your poloidal field. Maybe not the one you started with, but something like it.
What's the scale of the helical flows?
Oh, great question. Good. We'll get to that. I got asked that many times yesterday, too. Any other questions on this? It's spooky stuff. Does it make any sense? The twists and the... Oh, I love that. I'm getting some good looks. Okay, so let's do one more. Let's go back to that other drawing that I like. Oh, yeah, this is one from Paul Roberts that I like as well. There's your originally, let's call it toroidal field. It's kind of Cartesian in this sense. But he just pushes it up and twists, and he ends up with basically, he lets it reconnect right there. We don't have to, but we can. And now we end up with a little loop of current this way, or a little loop of magnetic field here, and the current comes out the center of the loop. So we've now generated an anti-parallel current system. And that's really what we need to finish the game. So I showed you before, omega effects take poloidal very nicely, very simply, into toroidal fields. And now, if you now let a bunch of helical flows interact with those fields and create these little alpha loops, as they're called, then you'll generate in the opposite direction some current, and that current loop now produces a poloidal field.
I understand that we don't know what causes this helical loop, but I want to know if they are just randomly, they could create the toroidal field that just cancel out each other, then you wouldn't have
You are correct.
Dynamo.
So
something has to organize it.
Oh, thank you so much. I can't. Yes, you're correct. That is exactly right. And that comes back to our lab dynamo problem. You go to lab dynamo, you have this thing ripping at 40 meters per second, but you need organized flow. How do you have organized flow at 40 meters per second? So, what's a great way to organize flow? What did I talk about yesterday? You rotate the living crap out of the system, and everything becomes incredibly well organized. And when you have that organization, it is actually very easy to have I should not say easy. It is not outrageous for a net dynamo effect to occur. However, you really set me up. As we look at the dynamos I'll show, they're all largely what I call well-organized or quasi-laminar dynamos. As you go to fully turbulent dynamos, they get hard. It gets harder to get those to work. And that's because as things become more turbulent, you need to rotate faster. But it becomes more expensive to numerically simulate rapidly rotating systems, and in the lab as well. How fast can we rotate? There are limits to that. So if you need 40 meters per second, you need your system, your system has to have a characteristic rotational velocity much higher than 40 meters per second. I don't want that in my lab. You'll end up on the New York Times for the wrong reasons. And you will. I mean, that's so dangerous. It's hard.
I guess the top loop, the direction is wrong, right?
Say it again.
The top loop.
Top loop.
You have two loops, right? Never mind. You don't have a citation anyway. So no, this one.
Go for it.
Right, this loop, the direction is wrong, right?
No, the direction's right.
Why it's right?
So look, this is coming down, and then you stretch it off to the side.
But that's a current loop, right?
No, sorry, these are all magnetic fields. My sincere apologies. No, this is just showing magnetic fields. Because in our world, if you look at that induction equation, you don't actually have to show J. No, my apologies. No, the alpha loops make magnetic field loops, and then the currents come out the middle. And so the current would be, if I remade this, we would make a different colored current loop going around any parallel. And that would generate poloidal field.
Yeah, I guess my question is really, when you talk about this vertical, vertical columns that you think that actually can generate this alpha, you call alpha loop. But what if you have this vertical columns with I guess you have omega, rotate this way, or you also, I guess you will also have omega rotated in the opposite way, right? Would you?
I don't exactly know how to answer that. Can I move forward and show you an example or two? Because I don't actually know how to answer that. But I will show you an example which maybe will show off roughly what I'm talking about. Yeah. Oh, wait, sorry, wait for it.
So when the poloidal field becomes toroidal, is there a reason to have a weaker field in the center of?
Oh, you mean in the center of the weaker field? This is actually just kinematics. All we've done is we've taken this initial field and we've wound it up. And so there's actually no winding in a sense. There's no field to wind right on the axis, and there is no winding occurring right on the axis.
But why don't you have just a cylinder? Or?
Why don't you just have a cylinder? I'm not sure what you mean. My apologies. Where are you looking for a cylinder?
Yeah.
There's no inner core here, if that's what you're talking about. I don't think I understand the question. Why are they coming in? That is a very good question, and I think the answer is I have no idea. I don't know why they're coming in. Actually, in my world, they don't need to. That may be diffusion. Maybe they put diffusion into their... Yeah, they have diffusion in their schematic, so I think it's actually diffusing in later. That's the only thing I can think of. I don't know why else. Yeah, I don't know. I honestly don't know. Without diffusion, I can't really change the radius without diffusion. But they have other parts diffusing, so maybe it's a diffusion thing. But I don't really buy that, honestly. There's something I don't get about it either. Because for me, they would roughly stay where they're being generated.
The lines that are closer to the axis to begin with wrap up at closer radius?
I don't think that should happen, honestly.
No.
I'm just telling the truth. I've done that problem a couple times. And when I did it in IDL back in the day, they didn't come in. So there's something else happening that I don't know about. So the question's a good one. I can't answer it. Not right now. But I think at 0th order, it's not our fundamental issue. Our fundamental issue is we want to come up with a way to take a poloidal field into a toroidal field and a toroidal field back to a poloidal field. So we've done that. We've gone poloidal to toroidal with the omega effect. And then we've gone toroidal field back to our initial configuration with this non-axis symmetric alpha effect. So that means we've gone full circle. So then we have a self-sustaining process. That's so relaxing. Everyone should be so happy. It's so relieving. So we've come up with a way to start with some field. We could have started poloidal, but we started toroidal. And as long as we can keep going back and forth to both, we're good. Because we have to, that's one of the hard parts of magnetic field generation. You can't generate the field component from itself. You have to stretch off to the side, so then you have to stretch from the other side. So you're always twisting and folding and stretching.
So I probably just missed something really simple here. But it seems that the axis of rotation of this rotating body will cause the poloidal field to align with the axis of rotation. But there's a misalignment on Earth. And so...
Because this is the absolute simplest system. This is a simple, right, theoretical,
so what is,
perfectly hypothesized system.
So what then causes that departure?
There are lots of ways to cause that departure, but let's go forward and we'll see that. And actually, I will show that in some Dynamo models, for instance, how you could have departures.
Just quickly, these little loops,
yeah.
Don't scream any good analogy for that.
I'm going to be technical, and technically no. And the reason I'm saying that, at 0th order, yeah, we want little eddies. The difference is those eddies are almost perfectly two-dimensional, right? While these are strongly 3D, I need three-dimensionality. Right. If I don't have three-dimensionality, I'm out of luck.
But they're currents that have cut off. And...
Yes. So yes, you've created loops, but you have to create loops in 3D. If there's no three-dimensionality, you're totally out of luck. So you can't have really a 2D dynamo. Any other questions? These are good questions. It's weird stuff. Yes? You're so flummoxed you couldn't even pass them.
What happens, if anything, at the very center of that sphere? Right? Is there any...
Very kindly, I don't really know or care. And I mean that. It's a fine question. In Earth's core, you have a big insulator, or a big conductor there that's solid. So you don't really have this process occurring in the Earth or in most planets with cores. There are dynamo models without inner cores. I don't know of anything that interesting happening there. Sometimes there's flow through the origin. Then you may get a different field morphology, right? You'll take your dipole and push it up to one hemisphere or the other. Then it's a dipole quadrupole like on Mercury. But I don't know if anything fundamental is happening there. I actually consider it the least interesting place, in all truth. Do you know what I mean? Like all the shearing is occurring elsewhere. It's very hard to get shear at your origin. Anybody else? Okay. Okay, so now we all get how dynamos work. I'm as happy as you are. And now let's talk a little bit about observations and models for the next 20 minutes or so. Okay, so here's some nice observations. This is the model from Andy Jackson, spherical harmonics out to about 13. As Matt just pointed out, it's not some smooth field. It's got all sorts of structure. It is dominantly axially aligned, right? Red means the field's coming out right now in the southern hemisphere, and it's dominantly going back in the north. But there are some pretty big flux patches. Some of them appear aligned axially. Actually, the two biggest ones, arguably, are aligned nearly axially. And then, and in addition, the other dominant feature I see is this equatorial wave train. So if you saw Nick's poster yesterday, there's probably some really interesting physics explaining the existence and the dynamics of those wave trains. Okay. And when we do simple models, this is from Krista Soderlund in 2012, you can roughly produce magnetic fields that look zeroth order, a good deal like what we see on Earth, right? We have some tangent cylinder, as we do near where these big flux patches are. And near it, we have big flux patches, right? And then we have other non-perfections in the field as well, right? So not everything. It's not this smooth field. So why is that? Well, in these models, this is a model carried out at an Ekman number of 10 to the minus 4, which means it's rotating rapidly, but the viscosity of the fluid is about 11 orders of magnitude higher than core fluid. So it's really viscous flow. And we get around that and create a dynamo by having a really high electrical conductivity of the fluid. But still, even in this very viscous fluid, we get beautiful columns. Coriolis is still dominant. It's still about 10,000 times stronger than viscous force. And so we get these beautiful columns. They're really large scale. And so we then have, from Uli Christensen's 2011 review, we have this. I would argue this is the present paradigm for the types of physics occurring in planetary cores. You have big columns. They're helical. You can see there's flow up and also around each of these structures. And those helices are really good at creating alpha loops. They're really good at creating dynamos. And so here's a nice paper, or a nice image from Julien Aubert. Give me one. Yeah, go.
I may have missed it. How did you generate the helices to begin with, or was it just turbulence?
Curses. That was all of yesterday. Yesterday was the helices. We are basically driving convection with a hot inner core boundary, cold CMB, and as that convection occurs, it still pays attention to this rapidly rotating constraint, and you end up with columnar structures. And those flows are helical. Okay. So we naturally have these rapidly rotating convective helices. There's one right there in the model. And if you look under the hood there in Julien's model, oh, that's awesome. We've got a poloidal field, and at the end of each of these columns, you have a massive alpha loop. It's huge. Can you guys see it? See, you've taken the magnetic field and you've wrapped it around. Those are alpha loops. And so there are two huge alpha loops at the end of each column, and associated with that is local magnetic field generation. So there's a magnetic flux anomaly right there. And so then we augment Uli's schematic, and we say, oh yeah, when we see these big flux patches, we're probably looking at the end of big columnar structures in Earth's core. Does that roughly make sense? That is the zeroth order argument. Yeah?
So, like a little bit too simple to be true. In terms of the dynamics of the...
That or me? I didn't know this would be so hurtful, Torsten. Yeah.
No,
keep going. Sorry.
The physics are fine. I don't know why you don't like the Rikki-Tikki dynamo, which is even easier to explain. But so what I mean is, in terms of being off, in terms of barometers, right? Do we still expect the large-scale flow structure to resemble that, or is there a worry that even the large-scale flow structure might be disrupted?
Good. I'm actually worried, so we'll head there next. You are 2 days in a row. Okay, but that is what I'm arguing, the present picture. Okay? And maybe I'm late on that. Maybe that's the present picture from 2010. I don't actually know when that is. You know what I mean? Maybe this is already a couple years old. But I would argue that's still the basic paradigm in the community. Okay? And so that's the paradigm, and I'm arguing, oh, look at that. Okay. So the paradigm at present, and again, maybe I'm a year or two late on that. People are starting to change a bit. But the present paradigm is that you have these helical columns, you extrapolate your models to planetary cores, and they do a pretty good job of being able to, we make models that can do a beautiful zeroth order job of explaining what we see. Good? Yeah.
So what we see is two of them. Mm-hmm. Why aren't there many all around?
To me, that's simply the schematic. I mean, it's simply the schematic. If you go back to Krista's image, there are many of them.
In the schematics, but in the Earth.
In the Earth, why aren't there more of them?
We see two of them, right?
You mean two dominant ones?
Yeah.
Yeah, that's a very good question, honestly. I think these are all good length scale questions. These are, for me, length scales come to the heart of it. What are the dominant length scales? And well, let's go to it now. Now you guys are doing a great job. So you're asking all the right questions, which means you totally get dynamos. It means I did a great job. Okay, so this is my summary before we go on. In a sense, summary number one is, this is what dynamos require. They require an energy source to drive flow. Those flows have to be well organized. If they're completely random, you can still get dynamo action, but it's purely small scale. You wouldn't observe it outside of, let's say, a planetary mantle. But there are astrophysical dynamos where it looks like you do have just small scale, just massive turbulence, and you get small scale dynamo action, but no large scale. Okay, so organized flow for planetary dynamos, conducting fluid, and you need large length scales. You have to have at least a two-stage regeneration process. If you don't have two-stage, you're out of luck. So, and in addition, somewhere you need non-axis symmetry in your system. Okay? Present paradigm, large-scale helical columns. And I think you'll see that's going to be changing soon. So I showed you before Krista's simulation from a couple years ago, done on, I think she did that on a 12-core machine. This is now a more recent model from Andrei Shaiko's thesis. I don't think he published it beyond that. But he was on, I think, a couple thousand processors at the Swiss Supercomputing Center, and this case ran for many months. Might have been more than a year, I don't know. But he's gotten now more extreme. So Krista's case was at an Ekman number of 10 to the minus 4. His case is down to an Ekman number of 3 times 10 to the minus 7. So he's actually more than 2 orders of magnitude less viscous in his fluid properties. And what do you see? You still see roughly aligned structures, but have they gotten smaller? Yeah, they have. And so let's play the movie. This is just a slice through his model, right? It's in the rotating frame, that slice, and you're looking at, you're looking at radial velocity. And so you see a lot of things are actually propagating through that plane. It's pretty cool. Is it different? Some people in the community say, no, it's the same old thing. It's columns. They're aligned. It matters who you talk to. And some people say, oh my God, it's fundamentally changing. These are much more narrow structures. Are they coherent across the shell? Do they reach all the way across the shell? A few of them do. A lot of them kind of break up. we're starting to get to what I call geostrophic turbulence, more what you see in the oceans, right? It's turbulent, it's messy, and yet there's a strong anisotropy to the flow. It's still well organized, but it's becoming a lot more complex.
Why don't you get the extreme reds and blues on the far left and far right limbs? It's all concentrated.
Good.
Mostly above and below the center core, and
yep.
And maybe just to the right and left of it, but not on the far left and right limbs.
I think you're right, actually. There's not very strong radial velocities here. It is a little easier to generate radial velocities that appear to be high inside the tangent cylinder. Some of that's just that he chose radial component, honestly. He has columns everywhere, actually. They may be stronger inside the tangent cylinder, and it's definitely easier to see them in the tangent cylinder because R is parallel to gravity there. You have to have flows in R there. So it's a good place to be to see them. What else do you see there? There's one other thing I should point out that I like in this model. If you look, let's use that. Look at that big dog. I keep saying everything's small. But look at, here it comes. Come on. Ooh, oh. Woo! What was that? What the hell was that guy? What was that? Neither do I. But I will. But I am proud and happy to hypothesize. So in rapidly rotating turbulence, one of the things you can do is you can start to grow turbulent structures. Turbulent structures can get much larger. Everything we've seen in our models to date are what I call the linear onset scale. They're what Chandrasekhar predicts from linear theory. They're very beautiful. But are they what you have in strongly turbulent planets? And so this is the first model I've seen where I start to see what's called an inverse cascade. Energy starts to go to large scales. You put it in at small scales, and there's coherency, there's self-organization, and you grow larger structures. So you see one there, and I think I see one there too. Go, come on. There it is. That looks a little bigger to me. So you might say, oh, you're a very hopeful person. I don't have any models yet that can live out here. This is super expensive to do. But I see hints. And
John,
so now, yeah.
You introduced the slide by saying as you decrease the Ekman number, the flow is changing. And you said people argue about whether it's changing. Does the magnetic field, or does B change less than V as you decrease the Ekman number? So that as you decrease the Ekman number, we see proportionally smaller changes in B.
Let me go to the next slide and show you B. I don't know the amplitude so well because it's not my simulation, honestly.
Does this field reverse itself?
I don't think so. That's because I don't know if it would or not. You know what's crazy here is? This is the problem I was mentioning yesterday. Even though he integrated for like a year, he didn't integrate for very long. It is so expensive that would it reverse? I bet it would. He had other models that did reverse. This one, I don't know. But this one, he couldn't integrate it for that long. It's so expensive. So now let's look at the magnetic field. That's the radial magnetic field on that same slice, same time frame, same everything. Anybody see columns? Yeah, maybe. Oh, there's my big dog. Wait. Oh, come on. Oh, how embarrassing. Okay. There it is. It's right there. It kind of passes in and out of the plane. So you see for a moment a large-scale structure. But is there induction all over the place? Yeah, there's induction occurring. But is it obviously, and it's a little washed out. It's about 3 times brighter on my screen. To me, it looks like there's nothing there. But there is something there. It's just not obviously correlated anymore perfectly with the columns. And if we now look at the surface field, again, I don't see obvious signs of columns. Maybe that's a column top. Maybe that's a top. Maybe. Possibly. Oh, maybe that. Instead, let's show it again. I do see that big vortex. Yeah. There's a vortex there.
Is this in some sense?
Wait, actually, Chris first.
So this is at the core mental boundary. So
That is
there's
the core mental
damping
boundary, sorry.
At the how would damping?
That's the next slide. So you're right on it. Did you have another?
Do we have some idea in what respect this may or may not be in a steady state, in a statistical steady state?
It is in a statistical steady state. He ran it long enough that it appears to be in a statistical steady state. That doesn't mean there isn't a longer scale behavior where it starts reversing or is reversing. If you look between reversals, you look like you're in a statistical steady state. So yeah, he did run it long enough to be in steady state.
And the amplitude fluctuations are sort of 50%?
I don't know what they are.
I mean, I've been trying to look at the BR scale.
Yeah, I understand.
It seems quite large. Is that?
No, I think that's about right. Yeah. Any other questions on that? Okay, so now let's do Chris's very sensible question. And let's just take a snapshot. I don't know exactly when that snapshot was taken. But here's a snapshot in time of that model, and this is Lmax. This is what we could see basically if we had data from this model, right? And we blah, blah, blah. The highest we can ever see is Lmax 12. So that's the core mental boundary field at the resolution we can see. All right. Does it look anything like Earth's field? Actually, it's not terrible. Were there any big structures in there? Yeah, there were a few near the pole, but for me, it's a different story already, right? It's rather different. So when you go to the present state-of-the-art models, it's not obvious that the flux patches are related to individual columns. They're not for me. There's still alpha effects and omega effects. It still looks like all this physics is occurring, but as I said, it's an ensemble effect. There's no problem with this occurring on very small scales, as long as it occurs throughout the volume. Does that make sense? And that looks like that's what's happening here. So to return again to Barbara's question about length scales, if we do, this is a figure I just made a month or two ago, and I'll put it out sometime this year, and its job is to get people annoyed at me. And it's showing these are the scales in the models. This is 10 to the minus 4 for the Ekman number. This is where we've been for the past couple years. Huge whopper columns. They look great. But as we head down to more extreme models, that onset scale becomes tiny. And this is following theory. I've actually plotted the diameter of these following Chandrasekhar. I'm very close. I'm within a couple of % of correct here and here. And the only incorrectness is I'm using plane layer theory in a sphere. But I, again, don't care at first order because it seems to work. But now lastly, if I go to Earth's core, they're gone. They're actually sub-pixel scale. It is the perfect example of a subgrid scale physics. So those columns may be there. But you literally, when I plot them in a vector format in Adobe Illustrator, they're just gone. There is something there. You can't see it. So that's interesting. To me, that means there's a change in physics coming, right? Now, one of the arguments people make, I sometimes make it as well, is that, well maybe it's because, yeah, the models are all right now very close to onset, but eventually we're going to become turbulent. And as we do, maybe we'll go to a turbulent scale. It doesn't care about the Ekman number. The Ekman number is proportional to the viscosity. But in turbulence, arguably, that we don't care about viscosity. This is just proportional to the velocity. And so this value is about 10 to the minus 6 in Earth's core. If we take the square root of that, actually, it's about that size there. Still tiny. You're still never going to see that. But what is interesting is, hey, we're doing models at 10 to the minus 7. We're going to be able to do that really pretty soon. So it's still touchy. You know, I still, when I even say that, go, ooh, we got to be careful. Because what I just said was, oh, if we can just get to here, And forget about all the subgrid scale physics that I don't understand. I'm sure we'll rock it. And that is dangerous. Think of our talk. Think of Patrick's talk. That would be like me saying, yeah, if I can just do a model and skip all the micro scale, I know I'll get it right. Huh? No, you need the micro scale. And there are a million problems. Same thing. You need to understand that physics. And it's the same thing with a GCM. It'd be like saying, I don't care about cloud microphysics. I'm sure I'll make good predictions. So do we need microphysics or not? I don't know. But I know this is already with respect to the observations microphysics, and we can get it within a couple of years. That's exciting. Then the next question is, we should also prove that we're getting the microphysics right. And that's going to take some more work beyond that. Okay, so how do we do that? Well, one of the things Emily Hawkins is working on, our big convection experiment at UCLA. Right now, it's the world's biggest rotating convection device. She just took data on this tank, 80 centimeters by 60. And she's been taking heat transfer and point velocities. And what we want to do next is get a particle imaging system so we can see the whole flow field and measure the length scales. Start to get the length scales and start to figure out when do we transition from a linear scale to a turbulent scale. What is the turbulent scale? There are a bunch of turbulent scales, honestly. I've just mentioned one. Okay? Then you say, yeah, but what about liquid metals? Oh, God, we've got another device for that. I'm going to skip this. Or I'll do it unbearably fast. The cool thing is when we do convection in liquid metals, skip that. Here's a time series on one of our thermistors. They start having these huge swings with little fast oscillations on top. You wouldn't see that if you put that in a quasi-steady flow like I showed you yesterday in water. If you put a thermistor in there, it wouldn't do much. It would kind of just have a little Gaussian shaking around. Here, it's just a mess. Sorry. Yeah, I told you I was going to do this fast. So fast, you won't know what I'm talking about. So here are thermistors inside our tank. You know what? I'm just going to skip it. We get big, crazy oscillations. That's all I'm going to say. And here's a view of the axial velocity field from a simulation of those rotating magneto-convection experiments. So now we're in gallium. We've got a magnetic field and a rotation. And we've got we're looking down from the North Pole. We've got kind of what you might think are columns, but now they're oscillatory columns. They're actually waves. They're actually pretty different. But what I see are big whopper wall modes. And so again, if you look at what Nick's doing, that's starting to show up. Those kinds of wall mode wave behaviors that it looks like you see in the data, they're showing up when you use liquid metals. And so there are lots of new modes that are just waiting out there when we go to more realistic materials. So we need to get a little lower in Ekman number, and we need to go, I think, to more realistic material properties. So re-summarizing, big columns to date. The ideas are right, I'm going to argue, at zeroth order. There's nothing wrong with the ideas of how a dynamo works. It's a little bit complex, but helical flow and some rotational alignment seem to explain what we see. Lots of open questions. For me, I'd like to know, what are realistic flow scales? What are realistic velocities in a realistically driven system? And how does dynamo action occur in turbulent flows of liquid metals? And just to point that out, simulations-wise, Nick Featherstone is doing a CIG project where he's going to be running about an 100 million hour simulation next year on the big device at Argonne. He probably will not get even to 10 to the minus 8. Even with that much computing time, he's probably not going to pull it off. But his code scales so far to 260,000 processors at about 80% efficiency. So we're not that far away from pushing down to these really small-scale turbulent processes. And the question is, as we get there, is there a paradigm shift? Do we change the way we're talking about dynamo physics? Fundamentally, no. I still know I need helical turbulence. But do we change the way we describe what's happening inside planets? Or am I just blowing smoke? And I actually don't know. I think it's a brilliant time to be doing dynamo research because I think transformations are coming, and it's research. We get to fight it out. So, thanks a lot. Yeah.
Okay, let me just ask a question that I don't know there's an answer to, but an effect like westward drift, could that plausibly be one of these transient upscaling turbulent effects on the right scale to give an apparent macro rotation of the whole field?
There are a whole number of ways to produce a westward drift. One of them is simply zonal flows. You can very naturally generate zonal flows. So in Julien Aubert's very nice model where it's depending largely on his intercore translation mode, if he has some asymmetry in the forcing, he naturally gets a hemispherical westward drift. That's very nice. Which again is why you see my people saying, oh, translating intercore is the way to go. Yeah, because his model is very beautiful. But is that realistic in terms of geodynamic constraints for intercore convection and seismic constraints? That's why I keep hammering at that one. That's the preferred model for explaining that, or one of. There are a couple others. Andy Jackson and Phil Livermore have another one. But there are a couple ways to do that. It's not usually an upscale physics. But there are now a couple ways. They're all interesting. It'd be nice to figure out who's who.
So if I remember correctly, yesterday you were talking about how you cannot reach a higher order in reconstruction or models of Earth's magnetic field, mostly due to the availability of data. But there are other models, there are regional models that use spherical caps, for example, in Europe, where I would assume you could reach higher order and smaller length scale. So how useful would those regional models be if they can be used at all to compare with numerical models?
If we could get smaller length scale, higher order information, it would be great. Even regionally, that would be wonderful. We're locked at about 12 or 13.
And do they
That's a constraint.
reach?
Say it again?
Do they reach higher order?
Do those models reach higher order? No, they can't. It's a downward continuation problem. It's just you have a potential field, and arguably you can't do that. You can't do better with a global scale spherical harmonic inversion. Maybe we'll get a little higher, but people have been trying for a long time. And it's really a geometric constraint, right? The mantle's thick. You've got a potential field.
And there's a crust.
Yeah, oh, sorry, I forgot to mention. Yeah, and there's crustal remnants. So, yeah, thank you. And so the magnetic field in the crust just takes over at about 12 or 13. So how do you get past that?
Okay, so maybe not a higher order, but more accurate description of how the Earth's magnetic field looks like can
if you
be
could
achieved
get,
if you use a regional scale model, right?
If you can do a regional scale model with higher temporal and spatial resolution, people will respond. I promise.
So I guess yesterday you mentioned about the possible effect from core-minor boundary.
Yeah.
Core-minor boundary topography and possibly heat flow. So we know that the core-minor boundary, all these features at the core-minor boundaries, actually they would have relatively large length scales, degree 2, probably. So I guess I see the need to go to really this very large fine resolution calculations that you suggest, to resolve these small length scales. Then I guess one question that I have here is really, to what extent do you think this core-minor boundary, long wavelength features actually will leave any imprint to the core convection and, especially in terms of length scales?
Mm-hmm. It's a good question. I don't know the answer. Well, let's put it this way. Over long time scales, there's no doubt core mantle coupling effects, right? And I think when you time average, you can arguably see core mantle coupling as well. But if I just look at, if I look at that, do I need any core mantle coupling? I don't know. So one of my questions is, how strong are the core mantle coupling effects? I honestly don't know. Again, when you look at many of the dynamical models, oftentimes you see people picking amplitudes that give them the answer they want because the amplitudes weren't well constrained. Maybe they're better constrained now. And many in my community would say, how could you say that? They would be pissed. But that's my opinion. When I see this, I sit there and go, I don't know. I don't know how strong those effects are. We may need them to get hemispherical westward drift. That isn't in this model, actually. But when I look at that snapshot, I wonder, what do I need? What don't I need? And so there's definitely core mantle coupling, but how much do I need it? I'm a little lost on that one. I'm very interested in that. I mean, I want to put more realistic core mantle coupling, thermotopographic into the models. Hard, but definitely worth it. Because I'm confused, actually, in some sense, how well that works. Time average, does that look right? With core mantle coupling, I think it does. Instantaneously, it looks fine. So then how important is it? I did not answer your question.
Can you say something about reversal frequencies or reversals in general?
Sure. Okay. At what do you want to know? There's.
Why are reversals every 500,000 years?
Okay. So 0th order. Actually, let's do the 0th order. So absolute 0th order. Let's go right back to our governing equation. That is a nice equation. So there's our governing equation. No dynamics at all. Let's just look at the induction equation. What happens if I stick in minus b? I have some b, some solution at some time. If I stick in minus b, is that equation happy? It's perfectly happy. It's linear in b. It's not a linear equation. It's massively nonlinear. But if you just look at b, yeah, fine, it's linear in b. So at any point in time, hypothetically, the gods Thor could come down and flip the field, right? How does it flip is the next level question. I'll say one thing. I don't know where this slide is. Great. When you look at the data, it's flipping much faster than the diffusion time. It's not a diffusional process. Reversals take about 3,000 to 5,000 years. Let's say 5,000. Whatever it is clearly shorter than the diffusion time in the system. It's not that the field is just, it hasn't given up hope. It's the other. It's that there's something strong occurring in the system that is dynamically flipping it. What is doing that, for me, is still up to grabs. If you look at that Aubert paper, I'm on that Aubert paper in 2008. We put out cute ideas for how it occurred. I loved our ideas. There are a million other good ideas. They naturally can occur in these models when you have strong nonlinear terms in your system. And that's no different. Again, you can think of these in a way as climate models. Just as you can see changes in regime in those models, you can have changes in these too. Does that answer your question? I didn't talk about time scale. I didn't talk about the longer time scale. The one thing I'll say about the longer time scale, that comes back to core mantle coupling. There is definitely a relationship between reversal frequency and CMB conditions. So you definitely see, the Cretaceous normal definitely has something to do with what was happening at the base of the mantle. So it's connected. How exactly, I don't know. There's some nice papers by Driscoll and Olson on that. The models are rather simple, but the arguments physically are still nice.
Any other questions?
There's evidence from meteorites for internally generated dynamos on planetesimals. Is there a paradigm for how those formed and operated?
So one, when you look at, those are awesome. That's when I heard that, I was about as happy as could be. That's just fun. Two, what's maybe more interesting in terms of the models we're talking about is on some of those planetesimals, you're actually hitting conditions where maybe you could simulate them a lot sooner, right? The Ekman number there, it could be about 10 to the minus 10. I looked at some of the numbers. We're not far from that. So we're not far from simulating those well. How do you drive those flows? That's really a good question. There's a nice paper, too, by Nimo. I think that's the first paper I saw on that I liked. I will mention, in those systems, that's where you might start getting interested in mechanical driving, right? Those are systems where, if they're very, very short-lived AL26 dynamos, okay, fine, they're thermal. If they're lasting longer, it might well be they're mechanical. Because if I can set up a small body with non-principal moments of inertia and slightly aspherical CMBs, it's really hard not to get mechanically driven turbulence. And in most of these systems, if you estimate the total rotational energy versus the total, let's say, thermal energy, rotational is much, much larger. So if you can harvest, that's what you're doing here. You're converting a little of the rotation into internal turbulence. If you can do that on those bodies, that's actually kind of a cool way to do it. And it would be probably rather long-lived, because it would take a long time to actually spin down that body or spin it out of that resonance. Do I have any proof for that? No. I'm just having fun. But they are really interesting. And they are a really interesting possibility for mechanical driving in addition to buoyancy-driven processes. Yeah, I'd like to see a mission to basically start to go look at those. It's a little embarrassing that there was no magnetometer on the Dawn mission. But that's the way life goes. Okay.
Okay, thank you.
Thanks. Thanks a lot. Whew.